Good evening, everyone. Thank you for joining us. I think we can start. Distinguished delegates, distinguished guests from China Association of Refrigeration, friends and colleagues, thank you very much for joining us to launch today a publication that comes at a very timely moment in a very timely region also. Dehumidification and air conditioning. Today, with our distinguished speakers, we will discuss science and technology, industry applications, and policy recommendations. Please help yourselves. The one-pager summary for policymakers is at the entrance. And for those who don't know IIR yet, IIR is an intergovernmental organization driven by science and technology of refrigeration, covering a wide range of temperatures from cryogenics to high temperature heat pumps. Today's publications and all IR publications are a result of international collaboration work where collective cross-border knowledge and science are generated. Our mission at the IR Secretariat today with my colleague Marco Duran here is to bring the voice of science to policymakers and industry, and this is our mission today. So now I would like to move to a short video introducing IIR.
The code is not just about temperature. The code is much more than that. It provides protection, preservation, survival. It shields vaccines so they can save lives. It keeps food fresh so nations can thrive. It powers industries, stabilizes nations, and sustains ecosystems. As the world evolves, decarbonizing heating is no longer an option, but essential for the energy transition. Heat pumps, as a true refrigeration technology, now play a central role in climate action. No longer just a resource, refrigeration is a critical infrastructure, essential for security, healthcare, and economic stability. The code moves in silence, acts in the shadows, sustains without seeking recognition. Without it, the world wouldn't function. The code must not only be stronger, it must also be smarter. Because the code is not a privilege, it is a necessity, a fundamental right that must be seen, understood, harnessed, and accessible to all. And that is where we step in. We, the IIR, are not just keepers of the code. We are the bridge between knowledge and action, science and solutions, research and reality. We don't just study refrigeration, we apply it. We don't just store knowledge, we pass it on. We don't just preserve the code, we bring it everywhere. We turn science into action. From scientific discoveries to real-world applications, we empower minds, we build skills, we guide to excellence, we support nations so that every country can master its own approach. Only then can the code become more than a resource, a true ally, the key to today's needs and tomorrow's destiny. Because the code should serve humanity, not just those who can afford it, not just those who have access to it, for everyone, everywhere. IIR. Science.
Thank you. Now we move with the first opening remarks with Mr. Wang from Deputy Secretary General of the China Association of Refrigeration and Senior Engineer for his opening remarks. Over to you, sir.
Okay, thank you. Distinguished colleagues, esteemed partners, and friends from the international refrigeration community, good evening. It's a great honor for me to address you on behalf of the Chinese Association of Refrigeration at this significant side event co-organized by IIR and CER. First and foremost, please allow me to extend our heartfelt gratitude to Professor Wang Baolong, Professor Liu Xiaohua, Dr. Monique Baha, and all the dedicated authors and editors involved in this landmark research report. Your tireless efforts and intellectual contributions have brought us this invaluable resource. We also congratulated the successful convening of this timely side event, which provides an excellent platform to unveil this research outcome to the world. Turning to the core significance of efficient dehumidification, its role in reducing global cooling energy consumption cannot be overstated. Air conditioning systems account for a substantial share of global electricity demand, and dehumidification is a critical yet often overlooked component. In regions like Thailand, where hot and humid climates prevail, the challenge is particularly acute. By improving dehumidification technologies and strategies, we can significantly enhance energy efficiency, reduce carbon emissions, and elevate stress on power grids. This is not just a technical advancement, it's a vital step toward sustainable cooling, especially for communities most vulnerable to rising temperatures and climate change impacts. The findings presented in this report offer practical solutions and insights that can directly benefit tropical regions, aligning with the global sustainability goals. Looking ahead, CER remains firmly committed to collaborating with IIR and other international partners to drive progress in sustainable cooling. Through knowledge sharing, joint research initiatives, technical exchanges, and policy advocacy, we aim to translate scientific advancements like those in this report into actionable solutions. China has made significant strides in cooling technology innovation and green manufacturing. We are ready to share our experiences and collaborate on global challenges. Tonight, we can accelerate the transition to more energy efficient, environmentally friendly cooling solutions that benefit all nations. In conclusion, let's celebrate this milestone achievement today and recommit ourselves to the mission of sustainable cooling. CAR is proud to be part of this global community working towards a more sustainable future. I wish this event a great success and thank you all for your contributions. Thank you.
Thank you very much, Mr. Wang. Now I will hand the floor to my colleague Marco Duran to hear more about the long-standing partnership between IIR and CAR. Over to you, Marco.
Thank you very much, Suhir, and welcome everybody. Thanks for joining us in this event. So just for context, and we will speak about this partnership and how the event came through today. China is a member country of the IAR, and the Chinese Association of Refrigeration, CAR, is the entity appointed by the government as the representative to the IAR. Founded in 1977, CAR is the National Scientific and Technical Association for the refrigeration and air conditioning sector in China. CAR serves as an academic and professional bridge in China's HVAC-R field, promoting scientific advancement, technical exchange, standardization, and international cooperation. It connects academia, industry, and government stakeholders, carries research, and organizes conferences, such as the Chinese Refrigeration Expo, that I had the pleasure to participate this year. Through CAR, Chinese experts, institutions, and industry leaders actively contribute to the IIR, commissions, working groups, publications, and conferences. And this collaboration enriches global technical knowledge and ensures that China's experience, data, and innovation are well represented in the international discussions. The IR is proud of our long-standing and productive collaboration with CAR, which we have jointly achieved, with which we have jointly achieved several important milestones, such as the organization of the IR International Congress of Refrigeration in 2007, the International Conference and Exhibition of LNG in 2019 Shanghai, the Conference on Magnetic Refrigeration at room temperature in 2024, and upcoming this year, the Conference on Phase Change Materials and Slurries for Refrigeration and Air Conditioning, as well as leading key publications such as the Data Center Cooling Technical Brief that was presented last year here at OEWG 47, side event co-organized with the CCAC, and today's, of course, air conditioning dehumidification technical brief that we are launching at this OEWG. So thank you very much, and we wish that you will enjoy the event.
Thank you very much, Marco. Now we will move to a more of context of the publication and the dehumidification conditioning technical brief. First, why this publication matters and why it matters to policymakers. Precise control of both temperature and humidity is fundamental to maintaining optimal indoor environmental conditions. And dehumidification accounts for over half of HVAC energy demand, according to IEA, which itself can represent more than 50% of buildings' total energy consumption in hot and humid regions. Beyond comfort applications, numerous industrial processes require strict humidity control to ensure product quality and process stabilities. Sectors such electronics, manufacturing, lithium battery production, pharmaceutical, and optical fabrication often demand deep and continuous dehumidification, leading to substantial energy consumption. Consequently, high-efficiency dehumidification technology are critical in reducing energy demand associated with air conditioning. Systems that specifically address temperature and humidity control can prevent energy waste incurred in traditional air conditioning by lowering humidity. After this general context, we move. So the publication today is published. This is the QR code. It's available in English and French. I would thank all the team that's been behind this publication, from editing to design to translation to French, to media and launch support, and to the organization of this side event. It comes also with a summary for policymakers, one pager, available in English and French too. Please feel free to download it, and the PowerPoint will be available after the side event. Now we move with the first presentation, air conditioning processes and dehumidification technologies, overview and comparison by Professor Zhang Tao from Tsinghua University. Over to you, Professor.
Okay, thanks everyone. I'm Tao Zhang from Tsinghua University, China, and I will give the presentation about the AC processes and the dehumidification technologies, the overview and the comparison of the report. So firstly, I think this is the weather in Beijing. I think firstly, I want to say where I am from. I'm from Beijing and also in China. But this page, I think we want to say that before Beijing is a city which is maybe in summer it's hot, but it's quite dry. Now I saw the weather here is that Beijing is now maybe it's similar to Bangkok here now. It's in July now. It's hot and it's rainy. It's a rainy Beijing now. So firstly, I want to say that the dehumidification is very important. Then secondly, I think this is 2 pages in I think maybe in home and also it's the window. You can see that it's it's very humid in the plum rain season in the Yangtze River. I think so. Dehumidification is also quite important. Thirdly, I should say that the load, the energy consumption, just as Soya said before, we can see that maybe the dehumidification energy can consume about maybe half of the AC consumption in the total energy consumption. So dehumidification is quite important. So I want to say that dehumidification is important. I think there's also a Chinese old saying that 重要的事情说三遍, which means that you can repeat one thing if it's important. You can repeat more than 3 times. So dehumidification is quite important. Then I want to share about the typical AC processes. So firstly, it's about the conventional AC system, which is conventional. It's handling the temperature and the humidity together. So we can see maybe the outdoor or the return air can be cooled and dehumidified where the moisture is removed. And then the supply air can be supplied to the indoor space. However, maybe there's some room which is a secret temperature or requirements. We should use maybe reheating is required. So there's energy waste in the reheating process. Then I give maybe it's an example about I think this is a kind of split AC air conditioner for the Europe, because now we noticed that in the Europe, now the weather is quite hot, maybe in France or in other European countries. We think this is a product from a Chinese company. It's called Media. So this is a kind of split AC air conditioner. So the principle of this kind of air conditioner is also the cooling or the condensation dehumidification method. Then we also give this is also an example about the home dehumidifier. It's use the cooling condensation method, but it can use the condensing heat to reheat the air. So the hot and dry air can be supplied into the indoor office. So this is a kind of home dehumidifier. And we want to see that there are also some problems with the conventional AC systems. We can see that there's loss in the coupled heat and the moisture handling process. And also there's energy consumption cost because due to the cold and hot heat offsite, which limits the dehumidification capacity. So we can go on about that. We can propose this kind of, it's called independent handling of temperature and humidity. We can also use this kind of method to treat the return air or the fresh air from outdoor. So we can use the cooling condensation method to handling the outdoor air or the return air, but we can dehumidify the air to a state, and also we can cool the air to a required temperature. So the temperature and the humidity control can be separated, and the energy efficiency can be improved. Then this is a figure about the independent method about the temperature and humidity handling process. So there's a humidity control subsystem, and also there's a temperature control subsystem. And we can believe that we also notice that this kind of independent control AC system is also be applied in the airport of Bangkok. I think we from the airport. So this kind of independent control of AC system with radiant cooling is applied in the airport of Bangkok. So we can further go on about the air dehumidification technologies, some different technologies. Here we use the air condition, for the air condition processes, there are air dehumidification technologies that can include the condensation method. This is the most widely used method now. And also it can include the liquid desiccant method and also the solid desiccant method. So we give the examples of these methods, and also we show this in the ID chart. Then about the condensation dehumidification method, we can see that it can remove the moisture by cooling air below its dew point temperature. And also for different processes, there's also energy efficiency. It's called coefficient of performance. It lies in different ranges. Then about the liquid desiccant method, it removes the moisture via direct contact mass transfer between the humid air and also other, maybe it's a solution. So use this kind of method, we can treat the air to direct the supply air temperature. Then here gives example about the liquid desiccant method. It's driven by a heat pump. So use this kind of heat pump driven method, we can use this kind of method to treat the humid air to required supply air temperature and humidity rate. Then about it comes to the solid desiccant method. This kind of method use the solid desiccant. The principle is about it's driven by the water vapor pressure difference between the air and the desiccant surface. So this kind of method can also driven by maybe a heat pump or other heat sources for the desiccant regeneration. Then there are also other emerging dehumidification technologies. For example, there are also electrolytic memory dehumidification methods. It also uses this kind of memory for dehumidification. Then there's also the hollow fiber method for the dehumidification, and can use different kinds of hollow fiber memories for the air dehumidification. Then we want to give some comparison about the air dehumidification methods. So we use this chart to give the comparison of the method. We can see that solid and liquid desiccant dehumidification methods can do, maybe it's called deep dehumidification, because the humidity ratio can be quite low due to this kind of method. Where the conventional, we call the condensation dehumidification method, can be treated the air to maybe it's about 10 to 8 to 10 gram per kilogram of humid air in the humid conditions. Then we come to that when we choose a technology for dehumidification, we can that we should take into account about the humidity ratio and also the required humidity ratio and the energy sources and also the economic constraints should be balanced. So finally, I give a brief conclusion and further perspective of the dehumidification method. So we want to say that dehumidification is quite important, and it's especially important in maybe Bangkok and in China and in other, in all the world. I think it's quite important. Then there are different methods for the dehumidification, but we should choose a proper method for dehumidification. For our home dehumidification, maybe the condition method is okay, but for other, maybe in the industry scenarios, we should use the liquid or the desiccant method now. So that's all. Thanks.
Thank you very much, Professor. I think thank you for the excellent overview. Before we move to the industry application and more example from concrete applications, we move to questions. If you have any questions that you want to now pose to Professor Zhang about the first part. Yes.
Thank you very much for an excellent presentation, and it's concise and clear. I've got a question on the types of humidifications that you talked about. You you sort of skipped quickly on solid gel or solid dehumidification. I suppose because its price is much more expensive than that of the liquid desiccant. And then you talked about liquid desiccant, and you explained that it's not anymore an emerging technology. It's rather an available, or rather a widely available technology, which is good. And then you talked about membrane technology, but you sort of didn't talk a lot about vacuum membrane technology. You talked more about two type of other technologies, membrane technology, but I wonder why you haven't talked about the vacuum membrane. That's one part of the question. The second part is nowadays with new advances in membrane technology, it's almost on the widely available. The way we used to, or we still are, dividing technologies on their appearance, not in kind technology, that is, in the RTOC. I'm an ex-member of RTOC. We start with research and development, and that may take 4 years or more, and then an emerging technology. And then once it's started to be manufactured, then it's available technology. And then if more than one manufacturer is doing it, then it's widely available technology. But I had the feeling, maybe I'm mistaken, that on the membrane technology, you haven't really talked about it being a widely available technology, although my knowledge is it's widely available. Sorry, it's a long 2 questions, but bear with me, please.
Okay, thanks for your question. But I think I can firstly answer the first question about the solid desiccant method. We think that for the solid desiccant method, you should firstly solve the regeneration heat source. Yeah. But the solid desiccant method, we think that it's proper, or it's quite good for some scenarios, because the battery industry, there's quite strict requirements for indoor humidity ratio. So the solid method is quite popular in that kind of scenario. And we use maybe electricity, or maybe it's a water vapor to regenerate the solid desiccant in that scenarios. But the energy efficiency is quite low in that scenario. So we should say that for this kind of method, although it's more expensive than the common method, but we can only use this kind of method in that scenarios for the battery industry. So this is just an example about the solid desiccant method. It's expensive, but there's some kind of scenarios that yes. So for the second question, I think that there are different methods for new technologies for dehumidification, and also in our group we also do some research about this kind of memory dehumidification method. But we also find that now if we compare the methods from the perspective of the energy efficiency, we should see that it's also quite low now, due to maybe it's due to the restrictions about the materials. I think here is also that the Professor Qian from Xi'an Jiao Tong University in China, he does some kind of new technologies for cooling. It's a solid cooling, maybe. I think now its energy efficiency is quite low. It's far away from the common cooling dehumidification method. But now he is also doing research now. So I should say that maybe we should do some more research about the new technologies for dehumidification. Thanks for your question.
Yes, can I just comment quickly? What you're saying is true, that the efficiency is lower than when you compare it COP for COP compared to mechanical vapor compression. But the thing is with dehumidification, new dehumidification, technology using membrane is that you don't use it on its own. It's part of a system, a hybrid system, where you add to it direct, indirect, evaporative cooling, and then you have liquid desiccant, and then they become much more efficient than mechanical vapor compression. This is the point I wanted to point it out, that you should maybe possibly look also at membrane technology as a hybrid technology, not on its own, because on its own it will be less efficient than mechanical vapor compression, of course. Thank you.
Okay, thanks for your suggestion.
Thank you very much, Prof. Ale and Prof. Chang. For now, we move to the second presentation. I think we need no more questions. Yes, I did not see the hand. Sorry. Please go ahead.
Mm-hmm. Yeah. Okay. Okay, thanks for your question. Firstly, I should say that maybe in your country, there's no need for dehumidification in summer. We think that maybe evaporative cooling is enough for your country. So this is for the first question. For your second question, it's we should say that for the solid desiccant method, the solid desiccant it can be regenerated. So there's no consumption for the solid desiccant. It should be regenerated after dehumidification. Yeah, it's a cycle. Yes. Thanks.
Any further questions? No? Okay. Thank you very much. Now we move to the second presentation by Professor Dr. Ma about emerging technology and industrial application. Over to you, Dr. Ma.
Okay, thank you very much. I'm Zhi Yao Ma from Tsinghua University, and I'm very honored to deliver this second speech talking about emerging technologies and industrial applications for the air dehumidification configurations. There are various types of the application scenarios requiring for air dehumidification, including the typical public buildings, such as the conventional office or commercial buildings, which has different heat and cold demand across different the climates. And there are also large space buildings such as the airport, the train station, or large sports arenas, which has complex heat and mass sources. And in these public buildings, there is often the demand for independent temperature and humidity control. And besides the public buildings, the industrial buildings, such as the electronic clean rooms or experiment element rooms, they often have a strict demand for constant temperature and humidity precision control environment. And other industrial scenarios, such as the lithium-ion battery manufacturing factory, in these scenarios, there is a demand for a very deep dehumidification demanding for a very extremely supply air humidity ratio. And in these public and industrial scenarios, the dehumidification may account for over 20% of the total energy consumption. Besides, apart from the conventional condensation dehumidification system, the liquid desiccant and the desiccant wheel systems are recently widely adopted by these scenarios for improving the dehumidification energy efficiency. And the two configurations of the dehumidification system have different technical characteristics and the application scenarios. First, I will briefly introduce the condensation dehumidification. It is the most widely adopted technology across the world, and it has large moisture removal capacity at the moderate dehumidification depth, such by treating the air from the outdoor humidity ratio to around 10 grams. However, it's the condensation dehumidification system often treats the cooling and the sensible and the latent load simultaneously, and the coupled cooling and the dehumidification treatment can cause severe cold and heat offset when the supply air humidity ratio is relatively low and the supply air temperature is relatively high, and it's not suitable for the independent humidity control. And in addition, the condensation dehumidification is also not suitable for the treatment for low humidity or deep dehumidification. And the liquid desiccant uses the liquid as the heat and mass transfer material between air and the liquid, and it handles latent loads by harnessing vapor pressure differences between air and liquid desiccant. The outdoor air is firstly cooled by the precoil and then passes through the dehumidifier for the air dehumidification, and the liquid solution cycles from the dehumidifier and the regenerator for the to absorb the humidity from the air and send the waste humidity to the waste air. And the system is this configuration is a heat pump-driven liquid desiccant air handling unit with the heat pump COP at around 426. And by further improving the energy performance of the liquid desiccant system, we can further changing the configuration from the single stage to multi-stage liquid desiccant configuration, and with the increasing cascading stage of the dehumidification processes, the regeneration temperature of the system can be further lowered, and this system can achieve a proper match between the inlet air and the liquid parameters by to further reducing the exergy discharge cost in the system to further improve the system COP by around 25%, and the system can be increased to around 7.4. And the liquid desiccant system can be applied in conventional public buildings, and this page shows a typical application in a office building in Shenzhen, China, which is a very hot and humid climate. The office building is originally used the conventional air conditioning system by substituted by the liquid desiccant based thermal independent temperature and humidity control system. The energy saving can be reduced by 35%, and the total energy consumption can be reduced by around 340 million watt hours per year in this 20,000 square meter building. And as we can see, the humidity treatment can be achieved by the liquid desiccant dehumidification. So, and the sensible heat can be removed via a sensible cooling terminal using the 17 degrees chilled water compared with the conventional 7 degree chilled water. The energy efficiency of the chiller can be significantly improved as a result. And this page further shows the application of the liquid desiccant system in a large space building, which is an international airport in Xi'an, China. And the airport terminal requires an independent temperature and humidity control. For the humidity treatment, the liquid desiccant dehumidification is used to treat the outdoor air from a very relatively hot and humid condition to a dry humidity ratio, and the dry air is supplied via displacement ventilation, and the sensible heat from the indoor environment is treated by radiation flow and dry FCU system. Using the heat pump-driven liquid desiccant system, and we can see the liquid desiccant can treat the outdoor air from the humidity ratio at around 18 grams to below 10 grams, achieving a dehumidification efficiency at around 50%. And the COP of the liquid desiccant system reaches 4.5. Compared with the other terminal of the Xi'an International Airport using conventional air conditioning systems, the independent temperature and humidity control system using liquid desiccant as the new HVAC configuration can achieve a energy saving ratio by around 36%. Apart from the typical public buildings, the liquid dehumidification system can also be applied in low humidity treatment industries. Here is an example in a printing factory using the cassava configuration of the liquid desiccant system with the supply air humidity ratio at around 3 to 4 grams. Below the required humidity ratio at around 6 to 8 in typical commercial or office buildings. And this system can be driven by a heat pump with the regeneration temperature at around 45 degrees, achieving a system COP at around 3.3 with 20 to 30% energy saving compared to typical air conditioning systems. And in this system, the liquid cycling performance has reached its limit with an optimal system performance for efficient low humidity dehumidification. However, for both the condensation dehumidification and the liquid dehumidification, these systems are restricted by saturation concentration of the liquid desiccant and freezing in low, and both water and liquid desiccant will freeze in low temperature. So these systems may not be able to treat the humidity ratio to a deeper level, like below the dew point temperature below 0 degrees, or the humidity ratio below 3 grams, or deeper level. The adoption of the solid desiccant system is now one of the major technical approach to achieve such deep dehumidification with the supply air humidity ratio below 1 gram or even below 0.1 grams. This page shows the typical configuration of the two solid desiccant dehumidification configurations: the fixed desiccant bed and the desiccant wheel. In the particularly for the desiccant wheel, the heat and mesh processes will proceed simultaneously in the highly combined channel coated with desiccant material, such as the silica gel or molecular sieve, to realize the air dehumidification. As the desiccant wheel rotates, the solid absorbent will absorb the humidity from the air to achieve the air dehumidification in the dehumidification side. And in the regeneration side, the solid desiccant is heated to a relatively hot temperature, and the desorption is achieved. And the humidity ratio is transferred from the solid desiccant to the regeneration air and exhausted to the exhaust air. And this page further shows the application of the desiccant wheel in a deep dehumidification scenario. This page shows a cascading 2 stages of the desiccant wheel system applied in a lithium-ion battery manufacturing factory, which has the demand for a very for a deep dehumidification treatment with the supply air humidity ratio below with the supply air dew point temperature below 0 degrees or sometimes below -3 to -70 degrees, and the outdoor air with around 20 grams humidity ratio. First, it passes through the cooling coil and then passes 2 stages of the desiccant wheel to achieve the low humidity treatment and deep dehumidification to around 0.01 grams with an dehumidification efficiency over 95%. However, the regeneration temperature can be reached over 100 degrees or even more. Thus, the system will are necessary to use steam as the heating source. The COP system can be reduced by is only 0.5 or 0.6 at the supply air dew point temperature of minus 40 degrees. Therefore, in recent years, coordinative optimization for the chilled water temperature and the multi-stage regeneration temperature combination via some model control strategies are proposed in recent years. And based on these strategies, the regeneration temperatures of the cascading desiccant wheel system can be reduced by to around 80 to 100 degrees. That's making the system available for driven by the high temperature heat pump. And the chilled water temperature is also can be optimized via the strategies. And these applications are newly developed model control strategies are also applied in multiple lithium-ion or semiconductor factories in recent years, achieving an energy improvement by more than 20% compared with the conventional two-stage of the desiccant wheel systems. In addition, as mentioned in the first part, the liquid desiccant system can show relatively energy efficient in the low humidity treatment. That's by in substitution to the first stage of the desiccant wheel, the hybrid liquid and solid desiccant deep dehumidification system can also be adopted in this environment, in these deep dehumidification scenarios by achieving the proper match between the dehumidification depth and the treatment process. The outdoor air is firstly treated by the most commonly used the condensation dehumidification for the moderate dehumidification depth, and then treated via the liquid desiccant for the low humidity treatment, and finally passing through the desiccant wheel to achieve the final stage of the deep dehumidification with the supply air dew point temperature at minus 15 degrees and the supply air humidity ratio at 1 gram. The COP can be driven by a heat pump, and it can be increased to around 1.8, and with the supply air dew point at minus 40 degrees, the system COP is also significantly improved compared with conventional systems, with an energy saving rate by around 24%. Commonly used solid desiccant system often use silica gel or molecular sieves as the absorbents, and in recent years, there are various types of the newly developed absorbent materials are researched in these years. For example, the composite absorbents or the metal organic frameworks. The composite absorbents can have a relatively large water uptake and can achieve a relatively lower regeneration thresholds. And the metal organic frameworks has tunable pores and stepwise absorption, which enables the dehumidification system working at a relatively low-grade heat. But however, for these newly developed solid desiccant materials, the application still need further research and further investigation. And I will briefly introduce other dehumidification technologies. This is in recent years, the electrolyte membrane dehumidification is also researched by some researchers. In this newly developed dehumidification technology, it can be applicable in the scenarios such as aerospace, power switcher cabinets, and high precision storage scenarios with advanced coating techniques. And for the another configuration of the Hobart fiber membrane dehumidification. It can achieve an isothermal dehumidification with high packing density, and it's also applicable in some scenarios such as green buildings or distributed HVAC systems. But for this newly developed dehumidification technologies, the application is not still not widely adopted in the actual practice. So the actual performance of this newly developed dehumidification technology still need further research and application. And in conclusion, in this speech, I briefly introduced some typical configurations of the dehumidification system and the application used in broad application scenarios. The dehumidification technologies are complementary to reconcile efficiency, dehumidification depth, and stability. In future, coordinated operation methods are still recommended for further improving the entry efficiency of the established dehumidification system via the improved of the configuration and the improved of the desiccant materials to improve their system efficiency for energy conservation. And that's for my today's speech. Thank you very much.
Thank you, Dr. Ma, for those insights on different emerging technology and industrial applications. Do you have any questions at this stage, or we move to the next? Yes, Professor Ala.
Thank you very much for an excellent presentation. It's very clear and concise, and I thank you. I just wondering one thing you said about saving of 25% on efficiency compared to mechanical vapor compression system on one of the liquid desiccant slides that you said. But you didn't mention the sort of ambient condition at which you receive this unit. Could you please elaborate and tell me what are the dry bulb and wet bulb temperatures that you had in mind? Thank you.
Okay, thank you for your question. For the liquid, I'll quickly go through to that page. The liquid desiccant system can substitute to the first stage of the desiccant wheel system. In the desiccant wheel system, required regeneration temperature can be relatively high at around 100 degrees, and in the low humidity treatment level at around 2 to 3 grams. For example, in this system, the outdoor air at around 20 grams can be treated to about 6 to 7 grams via the cooling coil, and then the air with the humidity ratio at around 6 to 7 grams can be then treated through the originally it's treated from through the first stage of the desiccant wheel to at around 2 to 3 grams, and now this stage is substituted by the liquid desiccant system. So the regeneration heat of the original system can be reduced the regeneration temperature of the first stage can be reduced from over 100 degrees to 60 to 80 degrees. So the system can be treated by a heat pump, and in substitution to the steam, so the system COP can be significantly improved, and the second stage is still the desiccant wheel to achieve the deep dehumidification from the humidity ratio at around 2 or 3 grams to less than 1 gram. Thank you.
Any further questions? Yes.
Because of the amount of energy they consume, or it is because of the cost. So, and also you talk about the disadvantage. What about the disadvantage? Like how often they need services? Maybe once in a week. I don't know, how often they need services?
Okay, thank you for your questions. Firstly, for the energy saving, the systems, dehumidification system of the actual industrial scenarios, the improvement of the energy saving mainly is because of the uh, the improvement of the cooling cooling temperature and the regeneration temperature. So the temperature of the cooling chiller can be improved via the liquid dehumidification compared with conventional cooling coils, and the regeneration heat grid can be also lowered by using the liquid desiccant in substitution to the solid desiccant. So the temperature differences between the dehumidification side and the regeneration side can be reduced, thus improving the energy, the COP of the energy systems. And for the industrial environment, for example, the lithium-ion battery manufacturing, this scenario, the dehumidification system will work like 24 hours, 7 days throughout the year. So like every single hour, every single minute, the dehumidification system will be operated. That's so the despite the summer or the winter. So the energy saving can be very sustainable throughout the years. And for like the typical commercial buildings or typical office buildings, the dehumidification system mainly will mainly be operated only in summer. For example, 3 months in a year, and working at the day. For example, like 9 o'clock to 17 o'clock, like 8 hours a day, and 3 months in a year. That's for the typical commercial or office buildings. But for the industrial buildings, the system may be operated like 24 hours, 7 days throughout the year.
Super. Thank you very
Thank you
much,
very
Dr.
much.
Mam. Now we move to the third presentation and we turn to an industry perspective. Please welcome Ms. Miki Yamanaka, Senior Manager, Global Policy Relations from Daikin, who will speak on industry perspective on dehumidification challenges and opportunities. Over to you.
Thank you very much for your kind introduction. I'm Miki Yamanaka of Daikin Industries. I'm Senior Manager of Global Policy Relations Division. So, I'm very happy to be invited by IIR and then also CAR to have this presentation. Thank you very much. So I'd like to introduce our approach to building decarbonization and explain our solution to prevent excessive cooling while saving energy while paying attention to balancing temperature and humidity at the same time. So please be relaxed. My presentation is quite simple, and then this is kind of the wisdom we got from the actual market. So please relax and then enjoy my presentation. So before we go into our solution, let me introduce who is Daikin a little bit. We are an air conditioner and a heat pump manufacturer and have business in more than 170 countries with 100,000 employees all over the world. So as our main business is cooling and heating, the Montreal Protocol is one of the most important international meetings. We would like to make utmost contribution to the activities, to the Montreal Protocol's activities. So now, what we would like to ask you here is that Have you ever felt too cold in your office, even though outside is really, really hot? So this is a typical picture you can see at your office, maybe especially in Asian countries. This is a common situation, particularly in Asian countries. Air conditioners are often set at around 23 degrees Celsius, and as you can see, many people wear jackets indoors, right? So in ASHRAE standard 55, the condition is referred as excessive cooling. So what kind of solution can address the issue of excessive cooling while maintaining the recommended temperature setting at 26 degrees Celsius? So this is a key point that we would like to solve. So we do not use any fancy technologies at all. We kind of combine all those technologies available in the market at this moment. So see, this is a conventional ventilation system, air conditioning setting temperature at 26 degrees. What's going to happen? So conventional ventilation system draw in hot and humid outdoor air and exhaust cool and dry air. As a result, even with appropriate AC temperature settings, it is difficult to achieve both comfort and energy efficiency. If we set the 26 degrees Celsius the temperature, the humidity can go up 60% or something. That is more than comfortable zone, so people will feel very uncomfortable. So now, when we look at the case B, that when we set the temperature like 23 degrees Celsius with conventional ventilation system, sorry, people often feel really uncomfortable, and then try to further lower the air conditioner temperature setting too much, which increases electricity consumption. Like this, right? So when the temperature hits 23 degrees Celsius, so humidity goes down further 50%, which is too dry. So people feel very, very cold. So people try to wear the jacket. So we wanted to do something with it. So now we have some solution using the available technology. We call it excessive cooling prevention system, ACECP. A bit long, but ACECP. So when we set the temperature of air conditioner at 26 degrees Celsius, so this system can maintain indoor humidity and temperature levels while ventilating. So like this, when they set the temperature at 26 degrees, but by using the ventilation system, energy recovery ventilation system, we can keep the humidity level at 55%, which is comfortable level. So our solution for excessive cooling, we would like to tell you this, that in conventional systems, hot and humid outdoor air is directly introduced into the room. So as a result, people often lower the air conditioner setting temperature to around 23 degrees, that is too cold, and then in order to feel comfortable. However, this increases electricity consumption and can also create an excessive cold indoor environment. And our solution addresses this issue while maintaining the air conditioner setting temperature at 26 degrees Celsius. The first step is the energy recovery ventilation system, as I said. By recovering energy from the exhaust air, let's go back to this one a bit. So there is no pointer here, right? So please go look at the above there. There is a box, and then there is a crossover of the air, incoming air and then outgoing air. So incoming air is kind of the hot and humid, but using the outgoing air, which is dry and cold, and then this is the exchange of heat and then humidity in that box, so that incoming air can have the lower temperature and then lower humidity, so which will lighten the burden of the air conditioner in the room, so which can cause the decrease of the energy consumption. So that is one solution. So this is the second rule. So by using this energy recovery ventilation system, we prove that 34% of energy can be reduced when comparing with the natural ventilation system. And then when we further go to the next device, which is called direct expansion coil as a cooling supply unit, this further improves humidity control and indoor thermal comfort. This is the third law. Energy recovery ventilation system with direct expansion coil as cooling supply unit, a very small unit. So, of course, direct coil, this cooling supply unit consumes some energy. So the, in total energy consumption, reduction can be same as the number 2 when singularly use energy recovery ventilation system, 34%. But if we combine further device, which is CO2 control, plus positive pressure control together, then the energy reduction can achieve 47%, while temperature setting maintains at 26 degrees Celsius. So that is what we would like to promote in the market, while using the available technology, not really difficult technology, but available technology, and then combine them and then control them together. That is the solution that we would like to offer here. So this is the demonstration project that we did in Thailand. So we wanted to evaluate whether what we are saying is really true or not. So we did the demonstration project. So to evaluate the effectiveness of ACECP under actual conditions, we carried out a demonstration project. So approximately 40% energy savings were achieved with the proposed ACECP system compared with normal ventilation system. Among the tested cases, ACECP provided the highest level of thermal comfort. Because the indoor condition remains mostly within the ASHRAE standard 55 comfort zone, with an average humidity ratio approximately 11 gram per kilogram of dry air at an air conditioner setting temperature of 26 degrees Celsius. So actually, we promote that kind of concept at the COP30 last year. We went to Brazil, and then we showed how it works. And then it was well received by all the visitors of the booth. So we would like to further promote this type of solution. I would like to call it as a solution. So, key takeaway here, excessive cooling is a hidden energy issue in hot and humid regions, as in everybody here talked about. And the proper humidity control can improve comfort while reducing energy consumption. The proposed solution had strong potential for decarbonization across Asian countries. I'm not talking about dehumidification, but in a balanced and a controlled way of humidity is very important. And then all those available technologies are mixed in a balanced way. That is very important for the market at this moment. Thank you very much.
Thank you very much. For the sake of time, I think if you have any questions, let's wait a little bit, 5 to 10 minutes. We have Marco's presentation with the recommendation. There is a question? No? Okay. Okay. Let's go now with Marco. We're going back to the publication, air condition, dehumidification and air conditioning, and this is IR recommendation and key actions for policymakers from the publication. Over to you, Marco.
Thank you very much, Suhir, and thank you very much for all and for your attention. I'm just going to walk you through the recommendation for policymakers that you have received, or that if you collected the page very briefly on what we're talking about. So we have the two recommendations on what we are defining as deployment and adoption. The first one, which is to promote the adoption of appropriate dehumidification technologies in tropical and high humid regions, of course. And then the promotion and support of demonstration projects, such as the one that was presented by my colleague Miki from Daikin. Then on market support mechanisms to provide financial incentives and subsidies to support deployment of these technologies. Standards and performance, advanced development of global air conditioning testing and energy efficiency standards. And then on innovation, smart control, increased support for research and development, of course, for the technologies that are not readily available or that are yet to be commercially viable. And then encourage the use of AI. On the promotion of adoption and demonstration of dehumidification technologies, I wanted to bring also some relevant initiatives or case studies of things that are currently happening in relation to recommendation 1 on adoption and then the demonstration projects. So in India, in Palava city, there's a field demonstration. It was a 9th-month real-world field demonstration program as part of the Global Cooling Prize, which is very advanced air conditioning units that that they operate for 9 months in these hot and humid operation conditions. These are equipment that are being, let's say, customized and tailored in order to perform like at the highest level and win this competition, but they demonstrated up to 60% lower energy use and reduced peak electricity demand compared to a typical air conditioning unit, combining systems that include dehumidification. And in Japan as well, besides the demonstration project that was presented by Miki, there's also the adoption of Daikin's Desica system, which has independent temperature and humidity control for energy efficiency, indoor and climate management, and is commercially deployed already in offices, factories, hospitals, universities, and so on, other buildings across Japan. For scaling deployment through policy and market support, the Global Cooling Efficiency Accelerator, who's the one responsible for the program in Palava city in India, funded by the Clean Cooling Collaborative and in partnership with the Rocky Mountain Institute. They have conducted this field demonstration, but beyond that, they have developed updated AC testing methods and performance metrics to better reflect temperature and humidity conditions control, which is not yet considered in the ISO standards that we have for MEPS, for example. And it is, and the humidification in the new, well, we will see that on the standards part, but like developing already testing and performance metrics in order to quantify how this equipment can perform, could be something we will be looking in the future to integrate in the different countries as well, because of the benefits that it has for electricity consumption and comfort, as we saw. Then on testing and energy efficiency standards, like a segue from what I was just mentioned, the new U4E model regulation guidelines just released this year for air conditioners and heat pumps. They have updated the performance metrics for benchmarking when we are trying to update or set up MEPs in different countries and energy labels. But they also now include these guidelines from the GCEA testing for considering the humidification performance for super efficient air conditioning units that are really effective in high humidity regions as well. So this is to intend to support the evolution of standards towards the technologies that we currently have. And lastly, on advancing innovation and smart humidity control solutions, on research and development and the use of AI as well for innovation. I just wanted to provide an example of a US initiative for R&D funding supporting advanced dehumidification technologies through the National Science Foundation and the Small Business Innovation Research Program. They have provided funding to continue advancing on the deployment of these technologies, and then the Helix Earth is developing a compact and high-efficient liquid desiccant dehumidification system designed to enhance AC performance as a hybrid solution. The technology uses this innovation desiccant regeneration process designed to reduce the energy intensity, as we saw in the previous presentations. And it has a retrofit design that enables its integration to existing commercial and residential AC systems. So they will be testing that, and hopefully will provide some good results so that it can be implemented. Thank you very much. Merci beaucoup.
Thank you very much, Marco. Now we move with the questions. If there is any question to Miki, Marco, or to the professors from Tsinghua University. Yes, Professor Ale.
Thank you very much, Ms. Marco, Mrs. Mickey. It's a very important point that is always forgotten. But I wonder, from the very start, why was there an overcooling in the space? Was that because the air distribution was not done properly to start with for the system? Or was it because some people were complaining and others felt a bit hot? The root problem you solved very elegantly by cooling air, all the exhaust air, you got it into a heat recovery unit or cooling recovery unit. And by doing so, you saved a lot of the energy. But to start with, was it bad distribution of air? Or was it actually an inability to respond quickly to indoor air changes?
Sorry, thank you very much for your question. That's I have to tell you that is all of what you said. I mean, but distribution of the cooled air, that is one thing that make people uncomfortable. So so some of the people try to make themselves comfortable, so that they try to lower the temperature, further. So some other people feel very cold, like me, and I feel really cold, compared to other people. So try to wear the jacket. That is the starting point. However, we found out that that is not only the it doesn't only the bad distribution of the cool air, but also humidity that matters a lot. If we control humidity at a very good level, or appropriate level, most of the people start feeling comfortable, even though the setting temperature is not that low. So the starting point is, as you said. However, when we further studying the phenomena, we found out that the humidity will could be the one of the key points of energy efficient, comfortable, creating energy efficient and comfortable air in the room. That is what our findings.
Mikel.
Yeah, thank you, Mikel Pitars from United for Efficiency. That we have developed the guidelines that Marco was commenting before. But my question is about the smaller units, like for residential houses. If these kind of technologies of dehumidification, they can be integrated also in these kind of systems, like smaller systems, and how this compare to the technology where you have like the heat exchanger from the air that is entering and exiting the room. Yeah.
For the household.
Yeah, for the household. Yeah.
Household. Actually, Daikin, as Marco introduced that we have the discount system, and then we use discount element. We how do you call it? We use discount element onto the some of our device so that temperature or humidity can be adequately controlled by that discount
Mm.
for household.
For
So
household.
for household. So that is equipped in the air conditioner itself.
Is integrated, all
Yes,
integrated.
yes.
So you
So
buy it directly and it's
right.
installed and it's
For the buildings like that, it can have such ventilation system
uh-huh.
and the air conditioner separately, so the separate control of latent heat and then sensible heat can be possible. But for the household, like Japan is very small house, so we cannot have both energy recovery ventilation system and then the air conditioners together. So we put them together by using discount element as professors explained.
Yeah, thank you.
Yes, then Professor Hade.
Okay. I look elder, so but I'm younger. What sort of desiccant are you proposing? Is that a dry desiccant wheel, or is it a liquid desiccant, or
Dry.
membrane?
Dry.
Dry. So it's a wheel actually.
No, that is how to call it, granule.
A hard coat
Desiccant.
silica gel.
Not silica gel, but discount how to particle.
Oh yes,
Yes.
lithium bromide probably. Thank you very much.
Professor Chang, you want to add something? No? Okay. Yes.
I think so, but I've never encountered such such case in my life, so I cannot say that is really right. However, I assume that is right. I would like to ask.
Maybe I can explain something because in the Yangtze River along the Yangtze River in China, also in winter maybe the temperature is below is higher than 0. Maybe it's about 5 degrees C or maybe higher than 0 degrees C, but the humidity ratio it's about maybe 80% or higher. So it's quite it's not good for the health. So maybe I'm not sure here or some of your body. Yeah.
Thank you very much. Any further questions? No. Super. We move now with the closing remarks from Ms. Na Tao from CAR, and she's the Director of International Cooperation. Over to you now.
Thank you, Ms. Sohail. Dear ladies and gentlemen, I'm Zhao Na. It's my great pleasure to deliver the closing remarks for this joint side event co-organized by the International Institute of Refrigeration and the Chinese Association of Refrigeration. This evening sharing has offered us brand new practical-oriented perspectives focused on the low-carbon dehumidification solutions. Professor Zhang Tao and Dr. Ma Zhiyao from Tsinghua University elaborated on the mainstream and innovative dehumidification technologies. Ms. Miki Yamanaka from Daikin shared industrial challenges and practical cases, and Mr. Marco Duran of IIR put forward feasible policy frameworks to accelerate low GWP refrigerant transition. The open discussion brought forward valuable insights on technology selection, climate adaptation, etc., which will greatly support the implementation of the Montreal Protocol. The joint publication launched today stands as a fresh landmark in the consistent collaborative bond between IIR and CAR. Moving forward, we will keep deepening bilateral exchanges, share China's low-carbon dehumidification experience globally, where IIR's network, and introduce the international advanced policies and technologies to facilitate domestic refrigerant phase-down and energy efficiency improvement. Once again, I would like to express my sincere gratitude to all speakers, participants, and supporting staff for your valuable contributions. We look forward to sustaining our regular dialogues and turning the consensus reached tonight into concrete actions to advance the sustainable cooling worldwide. Thank you very much. Thank you.
Thank you very much. Thank you all for joining us after a very intense day. Last but not least, I would like to invite you to International Congress of Refrigeration next year in Seoul, in Korea. Please join us. It will be a huge event, more than 1,000 participants to just discuss refrigeration and cooling and sustainability and very last cutting edge technologies. Thank you very much for joining. Thank you.